Okay, a scientist wishes to investigate the rate at which the mole grows on a slice of expired bread. So you need to take a look at the parameters here. So number one is the slice, one slice of expired bread, alright, growing of mole, alright. Right, so I conduct an experiment to measure the area covered by a mole on a slice of expired bread over a span of 2 weeks and record my findings in the table below. Right, so we have two variables. Number one will be t, right, the number of days, and number two will be x, which is the area covered by the mole. We got to calculate to correct to 4 decimal places the product moment correlation coefficient, otherwise you can say as R, for this set of data. Okay, so I explain why the value obtained in part 1 does not necessarily imply that a linear model is suitable for this set of data in the long run. Okay, part 1 is very straightforward, it's very procedural. So all I need to do is just key in a list 1 consisting of t and another list 2 consisting of x. So that's what we're right. Explain why the value obtained in part 1 does not necessarily imply a linear model is suitable for this set of data in the long run. So here, sometimes you really got to think out of the box. The context here, if you are talking about the number of days passed and the mole growing on bread. Okay, so a lot of people actually might actually miss out the fact that we are talking about one slice of bread. So we're talking about one slice of bread. What does it mean? It means that actually your area, right, is actually restricted. I mean, you have only at most, which is only one slice of bread, right? And then, so the slice of bread has a finite area. All right. So even though the product moment correlation coefficient R value here is close to 1, right? So even though, right, your R is close to 1, I mean the absolute value of R is close to 1, right? But a linear relationship okay, right, suggests that it means that there's actually no end. That means that the area, right, this area covered by the mole, right, it's going to grow indefinitely, right? It's going to grow indefinitely as the number of days passes, as the number. So you really need to write this amount, right? You need to write this amount to explain number days. So you cannot just write a summary. I mean, you really have to be very detailed as the number of day passes. All right, but however, the slice of bread only has a finite area. Has only as a finite area, right? So hence, a linear model may not be suitable in the long run for this set of data. Okay, can so that is the explanation for part 2, because here we must remember that the constraint is that we are looking at only one slice of bread, not infinitely many slices. Then the area will grow, but eventually it will stop because we only have one slice which has a finite area. Okay, right, so list 1 over here, I'm just going to key in list 1 consisting of t and list 2 consisting of x. So you can see that basically what I do, I just key in list 1, right? This is all my t, number of days, and this is my x, cm square, right, which is the area of mole. Okay, then simply I will just go to linear regression, step and press calculate number 8, and I have list 1 and list 2. So basically I am regressing the area based on the number of days, alright, because you can see that in this case the area depends on the number of days that pass by, right? So here I'm regressing line on x, so this is basically my list 2, which refers to x, and this here refers to t. This is the area of the mole, and t refers to the number of days, right? So next I'll do that, and I should have my right, my R should be equal to 0.95919. So this would be the answer that you get. Okay, so this is for part 1. Okay, and for part 2, 3, now part 3 suggests we need to calculate, after carrying out some work, the scientists theorized that a model of the form ln a over x minus 1 equals to a plus bt for some real constants a and b is a better fit for this data. He tests the theory out by calculating the r value between t and ln a over x minus 1. So it's a long question, take your time, highlight the main points, right? So we are basically regressing these two variables on each other for a few possible values of t, and I record my findings in the table as follows. Okay, calculate the value of r for a equals to 100. So what does this tell you? It means that you actually need to have one value, maybe that your list 1 need to be t, and your list 2 has to be your ln 100 over x minus 1. And that's what I will do, and we're basically going to use the same idea of creating a new list space. Right, so 1/6 decimal places because that is due to the question requirement. Right, so previous this. Alright, so over here, alright, remember that originally this was the number of days, right? This was the number of days, which is t, and here, right, this is basically the number of, what is this? This is actually the area x. Alright, so over here, right, what is list 4? List 4, I'm going to key in basically this 100 over x. So actually this shouldn't be x, this should be basically just list 2, right? Because list 2 refers to 100 over x. So key in ln L4 equals to ln 100 over list 2 minus 1. Alright, and you're going to get all the values as follows. Alright, with that, right, you're basically using correlation, okay, regression, or regressing list 4, which was the original value. These are all the data values of ln 100 over x minus 1, and list 1, which is t, that is the number of days. So we are regressing these two variables upon each other. Okay, and with that, the final answer should come out to be y equals to a plus bx, and your r value, your r square, to be produced from the GC. Okay, and easily your answer will just come out to be negative 0.9835. Okay, final answer negative 0.983563. Right, you write it to 6 decimal places. Right. Next thing, what we'll do, back to the question. If you go on to this question, you found that a is equals to 3.3689. So we just go use the value of a here and the value of b here. Alright, to just compare. Right, we know that from earlier on, right, the r value here, this as given, right, was found by us to be negative 0.983563. So we're just going to compare these three values, right? Which of 100, 101, 102 is the most appropriate value of a? Means I'm going to tell you which one is the best, the best model basically, or best value of a to put into the model. You can see that when a is equal to 100, alright, so again, the reliability of same, okay, the r is close to 1. Right? So you can see when a equals to 100, right, when a equals to 100, alright, gives the most, is the most appropriate. So y as the absolute value of r is closest to 1 out of the 3 values given, out of the 3 values. So you must state that it's out of the 3 values given, okay, because it may not be the most appropriate for all. Actually, in this case, it's the most appropriate because out of the 3, comparing the 3, is the best. Alright, so you make sure that you also write this. Okay, so part 4, okay. So over here, part 4, right, using the most appropriate value of a in part 3, find the value of a and b and use these values to estimate the least number of complete days needed for the mole to grow, cover an area of 50 cm square. So from earlier on, you have already actually used the value of a. So from earlier on, we already have the equation Alright, so we're just going to say very quickly, we use the fact that a is equals to 100. The regression line that we got, a plus bx would just be equal a plus bt, sorry. So it's a over x minus 1. This is the y, right? Remember the y inside equals to e. Okay, so let me just write this. Maybe I just write a ln 100 over x minus 1 originally is equals to 3.36839 from the one we found a minus bx, which is 0.631816t. Alright, so here estimate the least number of complete days needed for the mole to cover area of 50 cm square. So basically here x is equals to 50. So when x is equals to 50, now we have ln of 100 over 50 minus 1. That will give us to be equals to equate to 3.36839. So I'm sure here you are able to basically just solve for the number of complete days needed, right? So t is equals to 5.3313. Alright, after solving to 4 decimal places, and you can see that at least right, t 6, it must be equals to 6 lah, at least. Right, t is equal to, t is also equal to 6. Right, so you need 6 complete days. Alright, so for the next part,